So previous videos we talk about all these things and we say that we are left with whatever thing in the lecture 7. Transfer function, power gain, here and there. So what I'm gonna do is actually to start off with to touch on the rest of the chapter 7. So imagine you have a high pass or low pass filter or any amplifier or such. Okay, you have a V in, you may have a different V out, right? Because you may amplify it or you may have some voltage losses or what. So you have a transfer function of V out over V in this case. However, this can only describe only one significant frequency. This is only one voltage. So how do you describe the range of frequency in terms of this transfer function sum out over sum in? So in order to do that, we actually look into the transfer function of a high pass filter. Okay, so in this case, why is it high pass? We have a R1 connected in series with a capacitor, and actually they didn't draw finish this one, which is like a bit sad. So hold on a while. So in fact, you will have an R load over here, and this circuit, this graph shows wire voltage passing through this R load. Okay, and this is a very important thing that it always didn't show up. This is why it's very confusing. So R1 in this case is this. What I'm talking about? Okay, anyway, so this is a high pass filter if you remember the trend. So if a frequency is low, okay, if frequency is low maybe at this point, right? If this is 0, 1 divided by 0 is equals to infinity. So what does this mean? You have a very high impedance over here. High impedance over here, if you were to remember the rule, you wanna cause it to become open circuit, right? So all the voltage will flow through the R load. This also explains why all the voltage is flowing through the R load, and this is why the voltage is so high, because every voltage is flowing through the R load. This also I explained earlier. And then if your frequency is low in this case, let's say if your frequency is high, if your frequency is high, let's say this is infinity, 1 over infinity is equals to 0. So if this is 0, this capacitor acts as a short circuit. So it becomes a wire only. So all the voltage will flow through here instead of here, right? Given the analogy of you have a person over here, you have an obstacle, and you have a clear path. Will you want to go into here and then cross this obstacle, or you want to straight away here? Right? You definitely want to go over here, right? Because it's a straight path. So this is all the voltage will pass through here instead of here, unless a voltage like to do parkour. Yeah. So in this case, this is why at high frequency your voltage is 0, because there is no voltage flowing through the side. Every voltage will flow through here. So this is also one thing that, so in this case this is a high pass frequency, because it filters out all the frequency that is high, you see. So this is the key thing. And what am I talking about high pass? Okay, is that with understanding of this, then you can understand how the transfer function will work. So you know that V is equals to IZ, okay, where Z is equals to Z total is equals to ZR plus ZC, right? In series, right? In series. So it's the ZR and the ZC. So you want to find the current, and typically you will want to find the V out. V out across where? V out across this capacitor. Okay, it didn't specify which V out you're talking about. Right, V out over V in. It didn't specify which V out and which V in. So in this case, it's actually the V out across the capacitor or the V in. Why you want to choose the capacitor? Why you don't want to choose R load? The reason is because the only thing that is changing is actually the frequency of the capacitor. If you were to take note, the capacitance C in farad is always the constant, right? But however, the frequency you can alter along the way. Okay, you can change high frequency, you can change low frequency. So this is the reason why we only want to take note of the transfer function of the capacitor. In this case, the filter itself. So be very mindful of this. So without further ado, we shall start. So V equals to IZ. So you just bring the Z downwards, so you have I equals to VZ. So you know that the Z total is equals to ZR plus ZC, where R is just the resistance R is a real number, right? Because you will have zero phase shift. However, for ZC, you will have a 1 over 2 pi FC, right? This is the XC thing, right? And then you have a phase angle of negative 90 degrees, right? It's a lagging phase. So definitely, so if you were to, this is the polar form. If you were to change the rectangular form, you have zero real number because there is no real axis in a sense, because the angle is, you know, minus 90 degrees. So it's only in terms of the imaginary axis, which is going in this manner, 1 over 2 pi FC minus. So it's this sense, right? So these are all the thing. X as a revision for myself also. So yeah. So if you do that, I is equals to, so this is equals to this by simply changing this dude, okay, into this, and then you sub it in over here, right? So you know that I is this value already. So if you were to multiply with your ZC, okay, your capacitor impedance, you have a V out. This is why I say that you're talking about V out across the capacitor, not the R loop. Yeah, okay. So in this case, allow me to identify. So this is actually the ZC, right? Exactly the same, because 1 over 2 pi FC, negative 90 degrees phase. You have to change to rectangular, you have this form over here. Okay, and then this one is simply this one, right? I times ZC, so I is equals to this one. It's exactly the same thing, you see. So I just bring the I downwards over here and then I multiply with the current. Okay, so multiply with the impedance of the capacitor. So you will have this one. So after which, then I'll expand this one, so hold on a while. So let us expand with this one, because I just now used to go and check. So minus J, okay, 2 pi FC, multiply with V1, okay, R times 0 is equals to 0, right? And then R times minus J, you have minus J over 2 pi FCR. And then I'm simply doing this thing, okay? I'm simply multiplying. This is just the typical expanding system. So J 0 times 0 is actually 0. And then, yeah, plus 0. And then minus 0 times anything also 0. So this is 0. So if I were to clean it up, okay, I will have this one over here, right? And then if I were to further clean it up, I can actually cancel out the J, right? Because the J is at the numerator, right? Well, this one is simply put at is 1. Okay, sorry, my fault. I just realized something. Okay, I shouldn't multiply in. I don't know what the fuck am I doing. Seriously, I should just add them out together, right? If I add them up together, wouldn't it be great? I would have yeah. So let me simplify this one into this one first. Okay, let me fill out. So minus J times V1 is actually the top one, so it's alright. So the left the denominator, so 2 pi FC multiplied by, okay, R plus the real number is actually R. I don't know why I go and multiply. So J0 minus, away this is actually minus 1 over 2 pi fc j, right? So I can actually what do I do? Yeah, I can actually cancel out all the j, since you know that this I can actually feel, never mind, I'll just continue first. So minus jv1. So I multiply in the 2 pi fc, I'll have 2 pi fcr minus 2 pi fc over 2 pi fc. So you know that this is 1. So let me cancel it away for simplicity. So minus 1, okay, multiply with j over here. So you know that there is a minus j and there is a minus j over here, right? So you can cancel out. Then this also explains why we have v1 minus plus 1, because minus j and minus j cancel out, so we have a plus. So we have a v1 over this dude over here, right? My fault, I shouldn't cancel in that manner. I don't know what the fuck am I doing. Okay, this is j, right? So they are actually like that. I cannot cancel straight away because I think you know what I mean already. So what I can do is actually that I factorize out the j, right? Okay, I cannot factorize out the j. So this is the final form. What can I do in order to remove the j? Right? I cannot factorize out the j. If I factorize out the j, it will be very hairy. So what I can do is, you know that j square is equals to minus 1, right? So I can use this understanding to actually multiply with a j over j. J over j is actually 1, right? So if I multiply j over j inside, I'll have minus j square v1 over 2 pi fcr j, and then minus 1j square, right? So I think you need to really do this in order to know. I did a long time, but just by looking is really mind blowing already. Plus 1, right? J square becomes minus 1, so minus 1 is a plus 1, so this is also minus 1, so minus 1 is plus 1. So I have finally derived this one. So what can I do in order to reach this stage? This is actually your V out. So V out divided by V in. So actually I can divide this by the V1. Right, so this whole thing divided by V1, what do we get? Okay, so let me rewrite. So divided by V1 over here, V1 is simply V in, okay? This is the V in that I'm talking about, the V1. Right, so if I were to do that, I'll have 1 divided by V1, right? So if I cancel, I'll have 1 over this dude over here. Right, this is only for high pass, or nonetheless this is only for capacitor if you want to find capacitor. What if you want to find inductor? They didn't actually show you over here. So you're gonna take note. You're gonna find your own inductor. So hold on a while. In order to find what if it's inductor, okay, let us change this. So, okay, so this is inductor. Right, so I will change this format. So you just remember that this is actually for your capacitor. Right, so I'll just derive a inductor for you. Hold on. So similarly, V is equals to Ig, I is equals to you just bring the Z downwards, and then you can find your I, and then you know that in this case inductor is actually 2 pi FL, and then its phase angle is actually 90 degrees, so it's a plus. In this case, it's imaginary, right? It's going in 90 degrees. So this is actually 2 pi FL, right? So yeah. So if I were to, so this is simply this V total, alright? So I just simply change the V total into this one, and I sub in back here. Right? It's exactly the same thing, right? So let's elaborate on this. So this is I, this is the current across the resistor's inductor. So let me ask you, what is this actually? This circuit is actually a low pass RL filter, Okay, this is a low pass IL filter. So if you don't ask me why, you can just head back to the previous video and talk about it. But so if I were to do it out, I would have V1 R plus 2 pi FLJ. Okay, it's actually J. Alright, so this is my, after I sum them up together. So I can simply, this is I, right? So I can simply put over here because V equals to IZC, right? So this is actually my ZC. Actually this is ZL already, inductor. So this is actually my current, which is this one over here. So if I were to sum it out, okay, let's multiply this in. If I multiply this in, I will have 2 pi FLJ V1 over R plus, sorry, I will have 2 pi FL RJ plus 2 pi FL J square. Okay, that's a pretty hairy thing now. What am I talking? What the fuck? No, if I multiply this one on the numerator, I'll have only like that. Yeah, sorry, my fault. I don't know what the fuck I'm doing. So this is your V equals to IZL. So I want to find, this is the V out already, right? So this is the voltage out of the inductor, okay, across the inductor. So what I'm gonna do is actually to simplify the circuit to make it more cleaner. So what I can do is actually to filter up all the 2 pi FL in this case. So maybe I should write in different color. So I have a 2 pi FL J, okay, and then 2 pi FL J over here. So if I have to factorize out this one and this one, what I have within is actually V1 divided by R 2 pi FL J plus 1, right? And if I were to rearrange, this is actually V out, right? So V out divided by V in is actually times 1 over V in, right? So in other words, we know that V in is actually V1, right? So times 1 over V1, you cancel out the V1, and what you have is actually your resistors equation. So if you were to compare to your capacitor, what you have is actually a swap. So for the capacitor, you're gonna have 2 pi RC J together, while for inductor you have 2 pi FLJ below, right? So this is the concept that I want to convey, and take note that this J is actually in the denominator. Alright, it's not like that. Okay, it's like that. It's over here. So this is a very key concept. So I'll just stop here for transfer function. Alright, and then in the later videos we'll talk about the rest. See you.